Hello everyone, my name is Richard Xia, and today we'll talk about acid-base disorders. We'll talk about how to determine primary acid-base disorder, compensation, anion gap, and add-back method. So first things first, to determine primary acid-base disorder, you want to determine if it's alkalosis or acidosis, and if it's metabolic or respiratory. So to start, these are the normal values. Normal pH is 7.4, normal CO2 is 40, normal PaO2 is greater than 70, normal bicarb on the BMP is 24, and the normal ion gap is usually 12. So, to determine if it's acidotic or alkalotic, you want to look at the pH. So if the pH is greater than 7.4, then it's alkalosis. If it's less than 7.4, then it's acidosis. Next, you're going to look at CO2, and remember, it's normally at 40. So to determine if it's metabolic or respiratory, you're going to look at the pH and the CO2, and these two numbers can help you determine which one is which. If the pH is greater than 7.4 and the CO2 is greater than 40, it's metabolic. If it's less than 7.4 and the CO2 is less than 40, it is also metabolic. If the pH is greater than 7.4 and the CO2 is less than 40, and this is respiratory. If the pH is less than 7.4 and the CO2 is greater than 40, this is also respiratory. Notice how if the pH and the CO2 disturbance is going in the same direction, they are metabolic. And if the pH and the CO2 are going in opposite directions, then the disturbance is respiratory. And depending on the pH, it'll tell you if it's acidotic or alkalotic. So here you have metabolic alkalosis. This one you got metabolic acidosis, respiratory alkalosis, and respiratory acidosis. So this makes sense. In respiratory acidosis, you have increased CO2. In respiratory alkalosis, you have decreased CO2. So in metabolic acidosis, you have a decrease in bicarb, so that your body compensates by decreasing CO2. And in metabolic alkalosis, you have an increase in bicarb, so your body will compensate by increasing CO2. And that is because our body wants to be in equilibrium. Remember, CO2 is acidotic, while bicarb is alkalotic. Next, we'll talk about how your body compensates for your primary acid-base disorder. So remember, in metabolic acidosis, you have decreased bicarb. In metabolic alkalosis, you have increased bicarb. In respiratory acidosis, you have increased CO2. In respiratory alkalosis, you have decreased CO2. So this column shows what happens and how your body compensates in acid-base disorders. In metabolic acidosis, there's an expected decrease in PaCO2, and this is calculated by using the Winter's formula as shown, 1.5 times the bicarb plus 8. So in metabolic alkalosis, this is the formula to calculate the expected PaCO2. So it's the delta bicarb, so that means it's the bicarb on the BMP minus 24, the normal bicarb. And you multiply that by 0.6, and you add that to 40, which is normal PaCO2. So the rest expected compensation deals with respiratory. You have acute respiratory acidosis and chronic respiratory acidosis. You have acute respiratory alkalosis and you have chronic respiratory alkalosis. So if you can see here that 10 is always involved. In acute respiratory acidosis, the expected compensation is shown here. Here is saying the delta PaCO2 divided by 10 will give you the expected increase in the bicarb. So for example, if the CO2 is 60, so 60 minus 40 normal CO2 gives you 20. 20 divided by 10 is 2. 2 plus the normal bicarb, 24. So 2 plus 24 is 26. So the expected bicarb here is 26. And the rest of the formulas here are similar in terms of concept-wise. In chronic respiratory acidosis, the increase in expected bicarb is delta CO2 divided by 10 times 3.5. In acute respiratory alkalosis, the expected decrease in bicarb is delta PaCO2 divided by 10 times 2. And in chronic respiratory alkalosis, the decrease in bicarb is expected as delta PaCO2 divided by 10 times 5. And remember, normal PaCO2 is 40 and normal bicarb HCO3 is 24. So these, when it shows as a decrease or increase and increase, decrease, decrease, are deviations from normal values. So here is a normal value from 40, increase in here is from 40, this will be from 24, this will be from 24, this will be from 24, and here this is from 24. So the last column is asking if there's more acid base present in addition to the primary acid base disorder. If the observed compensation is not the expected compensation, it is likely that more than one acid base disorder is present. Observed equals measured on the ABG for CO2 and the BNP for bicarb. So if the measured CO2 is greater than the expected CO2, then there's concurrent respiratory acidosis on top of the metabolic acidosis. If the measured CO2 is less than the expected CO2, then the respiratory alkalosis is on top of metabolic acidosis. And for the difference in bicarb, we have to look at the anion gap, and then we'll use the add-back method, which we'll talk about later. For respiratory acidosis, if the measured bicarb is greater than the expected bicarb, then there's metabolic alkalosis on top of the respiratory acidosis. If the measured bicarb is less than the expected bicarb, then there's concurrent metabolic acidosis. And here, if the measured bicarb is greater than the expected bicarb, then there is concurrent metabolic alkalosis on top of respiratory acidosis. And if the measured bicarb is less than the expected bicarb, then there is metabolic acidosis. Next, we'll talk about anion gap. So normally the anion gap is 12, and the expected anion gap is usually 12. In a normal person, the albumin is about 4, so 4 times 3 gives you 12, and that's a shortcut. So the calculation for anion gap, you take the sodium, you subtract the sum of the chloride and the bicarb. Or you could just subtract sodium minus chloride minus bicarb. Should give you the anion gap. Albumin corrected anion gap. And this is important because patients in the hospital have low albumin, especially those in the ICU or those who are critically ill with sepsis. And it's important because most of this anion gap is made up of albumin that's in the blood. So if you have low albumin, you're going to have a lower expected ion gap. So to account for that, it's ion gap plus the value in here, which is normal albumin, which is 4, minus the patient's albumin, times that by 2.5, and you add that to the calculated ion gap, and that gives you a corrected ion gap. So for example, if the patient's albumin is 2, and their calculated ion gap was 12. So if you use that formula, you got 4 minus 2 gives you 2 times 0.5 is 5. So 5 plus the ion gap that was calculated, 12, gives you 17. So actually that patient's ion gap is 17. I also want to briefly talk about the osmolar gap. If the ion gap is elevated, consider calculating the osmolar gap if clinically indicated. For example, if you have a toxic ingestion, or if this elevation in ion gap is not explained by an obvious case, such as DKA, lactic acidosis, or renal failure. So here's the formula for the osmolar gap. It's 2 times sodium minus the division of glucose over 18 minus BUN divided by 2.8. And that is subtracted from the measured osmolality that's taken from the blood. The normal osmolar gap should be less than 10. Next, I will talk about the add-back method. And this is for metabolic acidosis with increase in anion gap. So if there's an increase in ion gap, we want to assess if there's another acid-base disturbance that's present. Remember, in our body, bicarb and H+ ions are at a 1-to-1 ratio because your body always wants to be in equilibrium. If there is a certain amount of increase in acid, there will be a same decrease in the amount of bicarb. So to calculate this, you want to first have the actual anion gap, which is your calculated anion gap, and the expected anion gap, so which is mostly 12 normally. So actual anion gap minus 12, and then you add that number back to the bicarb that's found on the measured BMP. And if that bicarb, the sum of that bicarb you get, if it's greater than 24, then that means there are more bicarbs. So there's a concurrent metabolic alkalosis. If the sum is less than 24, then that means there is decreased bicarbs. So there's a concurrent metabolic acidosis. Here's an example. Let's say the actual anion gap that you found was 17. Minus 12 gives you 5. And let's say the bicarb on the BMP was 14. So 5 plus 14 gives you 19. And this number is less than 24. Because you're expecting it to be added up to 24 since that's what it normally is in your body. If it's less than 24, then that means there's a decrease in bicarbs than you expected. So there's a concurrent metabolic acidosis. Lastly, I just want to go through an example of all the concepts that we spoke about so far. Let's say we have 7.2 pH. CO2, let's say, is 25. And the bicarb on the BMP is, let's say, 14. And let's say our sodium is 135. We have the chloride is 100, and then the bicarb we said was 14. And let's say the albumin is 2. Okay. So here first we want to determine the primary acid-base disorder. remember what I taught you. The pH is 7.2, so it's less than 7.4. The CO2 is 25, so it's less than 40. And so this means is metabolic. And since the pH is acidotic, so here we have metabolic acidosis. Since we have metabolic acidosis, the next thing you want to calculate is the ion gap. So 135 minus 100 minus 14, this gives you 21, right? And but remember, this patient's albumin is 2. So we want to use that formula again. We want to find the corrected albumin ion gap. So that's 4 minus 2 gives you 2 times 2.5 gives you 5. So you want to add this to the ion gap that you found. So that becomes 26. So this patient's ion gap is actually 26 when corrected for albumin. And the next step is using the add back method. Okay. So here we have the calculated ion gap, 26, minus the expected normal ion gap. In this case, since we already corrected for the albumin, we're going to use 12. So 26 minus 12 gives you 14. 14 plus here the bicarb that's on the BMP gives you 28. So this number is greater than 24, the normal bicarb. So since it's greater, there's more bicarb than expected. We say this patient has concurrent metabolic alkalosis on top of metabolic acidosis. In summary, today we spoke about determining primary acid-base disorder. And remember, normal pH is 7.4, CO2 is 40, then you have same change in direction of pH and CO2, it's metabolic, and a change in different direction of pH and CO2, it's respiratory. And we spoke about expected compensation. Remember again, normal CO2 is 40, and normal bicarb is 24. And we spoke about ion gap, normal of 12, and osmolar gap, normal is less than 10. And lastly, we spoke about the add back method. If the bicarb is less than 24, there's a concurrent metabolic acidosis. And if the bicarb is greater than 24, and there's a concurrent metabolic alkalosis. This is my reference. And if you thought this video was helpful, please like, subscribe, and look out for my next video. Thank you for watching.